Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to write work energy equations when the rotation of rigid bodies is involved. So what we're looking at here, this picture on the left here, we have a system that's got a mass A here, a mass B, and a pulley. And in this example, we're going to imagine that mass B is bigger than mass A, which means that if released from rest and barring any serious frictional forces, maybe where this pulley is suspended, mass B is going to start accelerating down, mass A is going to start accelerating up, and the pulley is going to have a rotational acceleration, or I'm sorry, an angular acceleration clockwise. What we're going to do here is we're going to try to write a work energy equation to find the speed of mass B when it hits the floor, or I said here the magnitude of V, and what I meant by that is the speed of the system. So basically we're going to try to find the velocity of mass B, the velocity of mass A, and the rotational rate of the pulley as B hits the floor if released from a height h. So I've already drawn my second picture here, but generally speaking, when you write a work energy equation, you start by drawing the system at a certain state. So this picture right here is going to be my first state. I'm going to call that state 1. Then you draw the system at the second state, right? And I've already went ahead and did that here. Here's my second state, so I'm going to label this picture 2. Velocity vector is very important. So in picture 2, mass A here is moving up with some sort of speed. Oops, I can draw a better vector than that. All right, let's call that VA2. Mass B is moving down. Now you notice there's a little daylight there, and that's on purpose because we're talking about just before it hits the floor. Mass B is moving down with a speed that I would call VB2. And then the pulley is also rotating, so it's got an angular speed, which is clockwise, and I'll just call that omega 2. Now, in this example, you'll notice that the radius, like the distance from here to here and distance from here to here, is the same. And what that means is that these two velocities are going to be the same. So I'll just put VA2 is equal to VB2, and I'm just going to shorten that to V2 now for the rest of the example. So, you know, this is not always true. This is a consequence of the radius being the same on both sides here. I mean, if this were some sort of cylinder that had like an inner and outer radius, or maybe a yo-yo or something, you know, these velocities could in fact be different. But in this example, they're the same. So we've got our picture 1. We got all the relevant info labeled, including this height here. We've got our picture 2. We've got all velocity vectors labeled. We've got a VA2, VB2. We've got our angular velocity vector. Now just write out the work energy equation. So we've got PE1 plus KE1 plus work equals PE2 plus KE2. Okay, now we just go through it term by term, just like always. So the PE1 term, if, you know, whenever we're dealing with potential energies, we have to define our datum. And I'm going to go ahead and define the floor here, the ground floor, as my datum. I'm going to go ahead and put a datum in green. I like green. All right, so there's my datum. And now, as we write our equation, mass A now does not have a potential energy. Mass B has a potential energy equal to mass BGH. The pulley technically has a potential energy within this datum, but no matter what I put for the potential energy of the pulley here under PE1, it's going to be the same as PE2. It's just going to subtract off anyway, so this is the only potential energy that needs to be considered. All right, this system starts from rest, no external forces, therefore the work term is 0. And again, let me talk about that work term. If we think about free bodies on the system, here there's a tension up, accelerating this guy. However, that tension does positive work on mass A, and it does negative work on the pulley. That tension, you got to imagine it's down here with the pulley rotating this way. So the tension on the left-hand side is doing positive work on this mass, negative work on the pulley. Net work done by the tension 0. Or another way to say that is that tension is an internal force, doesn't need to be considered. Same thing on the right-hand side. There's an external force applied at the pin on the pulley while this is occurring, but there's no displacement for that force, so it's not doing any work. So that's why that guy's 0. Now, potential work terms could come from, you know, if there were a frictional torque here, maybe applied at that pin, we'd have to include a work term, but in this example, I'm going to assume that away. All right, we'll look over here to the right. Under PE2, this guy's got a potential energy, M sub A GH. This guy at the datum, so its potential energy is 0. This guy's already been considered. All right, KE2. Now here's where this problem, has got some stuff to consider. So mass A has a kinetic energy equal to 1/2 mass A. Now normally I put VA2 squared, but I've already went through this, that VA2, VB2 are equal. I'm just calling that V2, so I'm just going to put V2 squared. Again, that 2 is because it's in picture 2. This mass also carries a kinetic energy, so 1/2 mass B, V2 squared. Again, if you want to put VB2, it's just fine, but later you have to recognize they are the same velocities. And in addition to that, the pulley now has a significant mass given in the problem in the upper right here. So it carries a kinetic energy as it's rotating. It's got a rotational kinetic energy. So we have a 1/2 I omega 2 squared for the pulley. So that's it. That's our complete work energy equation. About all we can do now is clean it up a little bit and then deal with this. So I'm going to go ahead and rewrite it. So we've got M sub B GH equals M sub A GH plus 1/2 MA V2 squared plus 1/2 MB V2 squared plus, now the pulley term, and I'm going to go ahead and do a couple things at once here. First, I'm going to take care of that I. This is presumably a disc-shaped object, so the moment of inertia of a disc is 1/2 mr squared, so we're going to have 1/2 times, and then our 1/2 mr squared is for the moment of inertia of the pulley. So that's going to be 1/2 mass of the pulley times r squared. I'm going to go ahead and deal with this now. I want to get this to one unknown on the right, so we've got V and we've got the omega. They're related by the rotation of the pulley here. So like at this point right here, V2 is up, and it's equal to R times omega 2 in this example. And that's true, if you consider this point as well. The velocity of this point is down, and V2 equal to R times omega 2. So in this spot right here, what I'm going to do is I'm going to put V2 over R. And that's being squared. So, a lot of problems the mass divides out. Here it doesn't, because these are different masses. We got mass A, mass B, and the mass of the pulley. But I do think what I'll do is start shifting terms over. So this term probably should go to the left. So we're going to have M sub B GH minus M sub A GH equals, all right, now V2 squared, V2 squared, V2 squared. We can factor a V2 squared out of that. And then what we're left with is, let's see, right here we're going to be left with 1/2 mass A. So I'll just put mass A over 2. Right here we're left with mass B over 2. And over on the right, being kind of cautious here, we have a 1/4. And then we have mass of the pulley. And you'll notice we have an R squared divide by R squared. So those are gone. Those are going to cancel. That's it. All right. So I think that's probably actually enough on this. The point of this video is how to write the equations. Suffice to say, this can be solved for V2. I mean, you can just put in numerical values everywhere, solve that for V2. A number would come out of it. So there's how we can get V2. And then once we want the rotation rate, we could take that right here, divide by R to get the rate of rotation of that pulley. Now, while I'm at it, I'm going to go ahead and talk about how would we use this velocity to now try to find the acceleration of the system. So again, this example, I've got to imagine this is a known quantities everywhere, fairly easy to solve for V2. I'm going to talk a little bit about what could we do with that now, but I need a moment to get rid of some stuff here. I'm just going to now take this, and I don't even have room to keep it, so let's see, what am I going to do here? We're just going to delete all that. All right, so now Again, I want to imagine for a minute that we have V2, known value. Known. All right, so now what can we do with that? Well, now we can use it to kind of analyze the motion. So what I'm going to do here, just kind of quick, is sketch a quick velocity graph. All right, so we're going to look at velocity against time. And right now I'm not going to worry about direction. We could talk about mass A, velocity up, or mass B, velocity down, and assign coordinate systems appropriately. I guess if we are going to talk velocity, we probably should do this. I'm going to go ahead and put like X, Y. So now we've got up positive, and my graph is going to be for this guy right here. And this velocity started at 0, ended at V2. Velocity is up, and I've got up positive. So when we sketch this graph, it's going to look something like this. Now, as far as how do I know it's linear, all right, so when you draw the free bodies, and hopefully we've seen enough problems like this, you end up with a constant acceleration system here when you go through and write Newton's second law equations. I think what I'll do is make a separate video about that, but for now, I'll just take my word for it. This ends up being a constant velocity problem. This distance on our graph would represent the time difference between position 1 and position 2. This distance on the graph is equal to V2, which again would be a known value. And then remember, when we analyze motion, the important concepts are slope and area. The slope gives the acceleration. So the acceleration of this system is V2 over t. And the area bound under the curve, this area right here, is going to give our displacement. Our displacement in this case is h, and that area is 1/2 t times V2. So, and again, that's coming because this is a triangle. Now, had this been some other curve, this would be some other type of geometry, and if this had been some sort of function, that would require maybe integration on the right-hand side. But this is just a nice triangular geometry, area 1/2 base times height. So again, if V2 were a known value and h were a known value, it's real easy to get t out of that. That would now be a number or a known value. That number can now go here, and we have a V2 here, so V2 over t would allow us to calculate the acceleration. I'm going to go ahead and stop this video right now, but there's more we could do. We could do a free body of mass A, write an equation with a known acceleration to get the tension. We could do a free body of mass B, write an equation with a known acceleration to get the tension on the right-hand side. An important thing to realize about this problem, the two tensions are not equal. We're going to have a T1 and a T2, or maybe T left and T right if you prefer, but an important thing to realize, these guys are not equal. And that's because if the pulley has significant mass here, it's going to take a difference in tension to accelerate it. So anyway, I hope this video helped demonstrate how to write Newton's second law equations for systems like this. Have a great day.